All right, this is Chemistry Chapter 9, Lecture 1. For this lecture, you're going to need to have your Chapter 9 notes out. We're going to go through the first 3 pages of your notes. You're going to want to have your book out, and Chapter 9 starts on page, looks like 285, and then have your periodic table ready to go also. No calculator. All right, starting up at the top of your notes. So we're talking about polyatomic ions, and polyatomic ions are formed when a group of atoms gains or loses electrons. So our first polyatomic ion we're going to talk about is hydroxide. Okay, you might remember seeing that when we were balancing equations in Chapter 4 and Chapter 5. So we have an oxygen, and let's draw the Lewis structure of that. It is in column 6 on your periodic table, right? So it'd be like that. And then hydrogen in column 1 would be like that. So hydrogen can form a covalent bond with that oxygen. So you'd have something that looks like this. All right, but we still have an open slot. So hydrogen has 2 electrons, oxygen has 2, 4, 6, only 7, and it desires to have 8 electrons in its outer shell. So let's say a sodium comes along. So we're talking about the ionic compound sodium hydroxide. So let's say a sodium comes along. It's in column 1, right? Column 1. Okay, has 1 valence electron, and it wants to give up that electron, right? We'll just draw, instead of the plus, we'll draw that electron there. And so it is happy to give that electron to the hydroxide in the open slot on the oxygen. So what you have now, oxygen's happy, but because it has an extra electron, all right, it has a negative charge. It was neutral before, now it has a negative charge. It gained an electron. Sodium has a positive charge because it lost an electron. And so an ionic compound will form because those two will be attracted to each other through opposite electrical charges. Okay, so the interesting part about polyatomic ions, hydroxide is an ion because it has a negative charge, but it also contains a shared electron pair. Okay, it has an electric charge like an ion does, but also has a covalent bond. All right, let's look at another one. Our other example is carbonate. All right, it has a symbol of CO3 2 minus. Okay, so carbon would be in the center, right? It has 4 valence electrons. And then we have 3 oxygens to fit around it. Well, one of those oxygens would be able to have a double bond, but the other 2 would only be able to have a single bond because carbon only has 8 slots, right? So this particular oxygen is happy because 2, 4, 6, 8. All right, but the other 2 aren't able to achieve their desired octet rule. Okay, so you have carbon's happy, this oxygen's happy, but we have 2, 4, 6, 7, 4, 6, 7. So we have 2 open slots, one here and one here. All right, so carbonate must snatch 2 electrons to have its ideal configuration, or most stable configuration. Okay, so carbonate would need 2 sodiums to come along to get an electron there and then an electron there. All right, so go ahead and pause the video if you need to. All right, and we'll move on down the notes to the table on the first page. So in our class, we're going to be working with the 14 most common polyatomic ions. Now it says on here that you must memorize, and eventually I will make you memorize it. But for the test, I will give you a sheet that has the name, the symbol, and the charge. But eventually we will have a quiz where you have had to learn these, okay, kind of like an element quiz. All right, so these are the 14 common ones that we're going to be working with. So you'll be as we go through the on your own, you'll be referring back to this table and also on your homework. All right, open up to page 289. And we'll work the 3 on your own problems there. So the first one, we just need to balance the chemical equation that has polyatomic ions in it. So barium nitrate plus sodium hydroxide makes barium hydroxide plus sodium nitrate. Okay, and so what you want to do to balance these, if you remember, is just leave these polyatomic ions, these chemical formulas inside of parentheses, as a unit. Don't try to break it apart into nitrogen and oxygen. Leave it as a nitrate. So we have 2 nitrates here. We only have 1 on this side, so let's put a 2 in front, and now your nitrate is balanced. We have a 2 in front of sodium now, so we need a 2 here. And that takes care, now we have 2 hydroxides, the OH, we have 2 right here, so that takes care of the balancing for 9.1. 9.2 says we want to give the chemical formula of the following. The first one is potassium sulfate. All right, potassium is in column 1 of the periodic table, column 1 here. So it has 1 valence electron. It's a metal. It wants to lose that, and it would attain a positive 1 charge. So we're just keeping going with our chapter 8 material. Sulfate, if you'll look in the table, has a formula of SO4 2-. So use the same rule. We'll just take the superscript and make it a subscript, right? We just do the big switcheroo here. And this is a 1. We bring it over there. Of course, we don't really have to write a 1. And that's going to end up being K2SO4. Since it's only a single SO4, we don't need to put parentheses around it. All right, the second one that we are going to do is ammonium carbonate. All right, ammonium, if you will look on your table, is NH4+. Okay, so it's just one of the famous polyatomic ions on your notes. Carbonate, we've already looked at that, CO3, 2-. So let's bring that 2 over here. We'll bring that 1 over here. And I would have NH4, 2, CO. Well, excuse me, I forgot the 2. NH4, and since it has more than 1, we need the parentheses, 2, CO3. All right, and C is aluminum acetate. Right, aluminum is in column 3. 3 valence electrons. It wants to lose all 3 since it's a metal, so that would attain a 3+ charge. Acetate is a polyatomic ion on the list on page 1 of your notes, C2H3O2-. Then we're going to move that 3 down here and move that 1 down here. So we have Al, C2H3O2, 3. All right, so just like we did in Chapter 8, except this time we're dealing with polyatomic ions. All right, go ahead and pause the video if you need to finish writing that. And let's do 9.3. Okay, so 9.3, just reading through that text there, says when aluminum nitrite, so I'm going to write all these out. Aluminum not nitrate, nitrite, reacts with sodium carbonate. All right, you get aluminum carbonate and sodium nitrite. This is called a double replacement reaction. We'll learn about that in Chapter 16. All right, sodium nitrite. So we want to balance this. Write out the equation and balance it. Well, first of all, we have to get the proper compound. Aluminum, we've talked about that quite a bit. In column 3, it's a metal, 3+ charge. Nitrite, if you look on page 1 of your notes, look in the table, it's NO2-. Sodium's in column 1, right? So it has a plus charge. Carbonate we've talked about a little bit, CO3, 2-. Aluminum, again, 3+. Carbonate, CO3, 2-. And then sodium would be, and then NO2-. So now we need to just put them together, bring that 3 down here and the 1 down here. We'd have Al, NO2, 3. And then Na2, because we're going to bring that 2 down here, CO3, because we need 2 sodiums to fill those 2 open slots in carbonate. And then after the big switcheroo here, it'd be Al2, CO3, 3. And then they're both 1, so we can drop it. It's just going to be Na, NO2. All right, that was all the work. Balancing's easy. All right, so I got 3 NO2s here. Okay, I've got 3. Let's put a 3. Let's see. I know I'm going to have a 2 for the aluminums. All right, and I know I'm going to have a 3 so that carbonate is balanced. There's 3 of those. That makes me have 6 sodiums. All right, and I think that will do the trick. All right, so 2, 3, 1, and 6 for that. All right, that covers page 1. Now we're going to move to really a totally different topic. So if you'll turn to page 2 and pause this if you need to finish writing. All right, most of the rest of this chapter is about molecular geometry, just the shape. So if you like art, then you might like this section. You can do a lot of drawing. Molecular geometry, the VSEPR theory is how it's said. VSEPR is how it reads phonetically, but VSEPR is the way it is pronounced. Valence shell electron pair repulsion. That's what it stands for. The theory is that molecules will attain whatever shape keeps the valence electrons of the central atom as far apart from one another as possible. Molecules are not flat like Lewis structures. They have a 3D shape. So we've got 5 shapes I'm about to go over: tetrahedron, pyramidal, bent, trigonal, and linear. Okay, so the tetrahedron shape, I have a model here. I hope that you can, from the overhead camera, kind of see what's going on here. So the tetrahedron shape has one central atom surrounded by 4 atoms with 4 single bonds. In order for those outer shell electrons to get as far apart as possible because they're negatively charged, then these will assume a shape, a tetrahedron shape that has 109-degree bond angles. Okay? The angle between there and there is 109. Between there and there, 109. All of them, 109. Okay? So the way that you draw these, so an example of the tetrahedron shape would be CF4. Okay, so if we were doing like chapter 8 and just drawing carbon has 4 valence electrons, fluorine has 7, just needs 1, so it would look like this. But in chapter 9, we want to show the shape. A central atom surrounded by 4 single bonds. So the way we would draw that tetrahedron shape is we put that carbon in the center. We would have 1 fluorine on top. And then we would show like that. The one in the center we show with a very thick line that kind of looks like a necktie. And then we show one with a dash line. And so you have to draw it this way. That means it's going behind. So it's kind of a 3-dimensional attempt. Go ahead and put all the electrons. All right, so this is the tetrahedron. And you need to memorize the name and the bond angle. So that 109-degree bond angle would be that angle. So all of them. So you don't have to mess up your drawing with that if you don't want to, if you understand what the bond angle is. All right, but 109-degree bond angle. Okay, that's our first shape. Our second shape is the pyramidal shape. So a pyramidal shape, hopefully you can see this, it's like a tetrahedron, but you took the top off. All right, so you end up like this. So I hope that you can see the 3D nature of that from the overhead camera. So it just makes a pyramid. Okay, pyramid like that. All right, so what it has is a central atom surrounded by 3 atoms that have single bonds. Okay. So an example of pyramidal shape is NH3. The central atom would be nitrogen. Nitrogen's in column 5 has 5 valence electrons, so you'd have 3 single bonds with hydrogen. So the way that we would represent that, you've got that heavy necktie looking line coming out front, the dash line in the back. You still have 1 electron pair still attached to nitrogen, because remember nitrogen's like this, right? So that pair right there is right here. The bond angle is 107 degrees. So why is it 107? Well, this electron pair influences the bond angle and squishes these bonds down just a little bit, another 2 degrees from the tetrahedral shape. All right, so that electron pair influences the bond angle, squishes it down just by 2 degrees. All right, that's pyramidal. We're still on page 2 in your notes. The third shape is the bent shape. Okay, you will have a bent shape. Let's see here. Well, it looks like I did not bring the bent, but I can make one real quick. All right, this is the bent shape. Okay, it's when you have a central atom surrounded by two atoms with single bonds. All right, so pretty straightforward. The most famous bent shape is H2O. All right, so you know, oxygen, if we were just drawing the Lewis structure that we did in chapter 8, you know that it would be something like this, right? And you'd have a couple of electron pairs around that oxygen. Well, what ends up happening with the bent shape, so that these can get as far away apart as possible with those electron pairs, is you end up having this situation. All right, let's sorry about that. I'll leave a little space there. All right, so these electron pairs squish down even further. Voice cracked. Bond angle is 105 degrees. So for the bent shape, you need to memorize that the bond angle is 105 degrees, and it's a central atom surrounded by two atoms that have single bonds. All right, that's 3 out of 5. Turn the page in your notes, and we will do the last 2. All right, the fourth shape is trigonal. It is also called trigonal planar. All right, so here's an example of trigonal. The reason it's called planar is that it's in a single plane, all right? So it's more of a two-dimensional type shape. It will have a central atom, two atoms that are tied to the central atom with single bonds, and then a third atom is tied to the central atom. These springs represent a double bond, okay? Boing, all right? So that's the trigonal shape. An example of the trigonal shape is CH2O. Okay, the carbon is in the center. You know that hydrogen can only take a single bond. And we could draw this oxygen in any of these three spots. And then oxygen can take a double bond because it has those two open slots. And this is, think of this kind of like a circle. A circle has 360 degrees, if you remember that from geometry, so each bond can be 120 degrees. Because 120, 120, 120, 120 be 360. So remember, these bonds are trying to get as far apart as possible, as far apart as the geometry will let them. And so with in a single plane, you can go 120 degrees if you have 3 bonds. All right, finally, the last shape that we're going to talk about today is linear. All right, the linear shape is exactly what you think it would be. You can have a single bond. That is, looks like barbells, right? All right, single bond between two atoms. That's linear. Or you could have a situation like carbon dioxide, where you have a central atom and surrounded by 2 double bonds. Okay, that would also give you a linear, or just think of it as a straight line shape. All right, so CO2 would be like this, which I believe we drew that in chapter 8. Okay, you want these bonds as far apart as possible. There's no unpaired electrons or electron pairs around the central atom that are influencing the shape, so they can get as far apart as possible if they go 180 degrees. Another example of linear would be like what we talked about in chapter 8, just nitrogen. And so you had 2 nitrogens with a triple bond. Well, that's a linear shape also. So is O2. That's a linear shape. All right, so anything, and then even H2. That's a linear shape. Okay, so simplest, easiest is the linear shape. I'm going to stop there. At the bottom of page 3, I have all of this in a table. It may help you to read through this table and to kind of, it's just a summary of all this, or that might not help you at all if you don't learn that way and you want to go back and look at the pictures and draw those out as you drew out in your notes and look over those, then that's a great way to learn it as well. But this is just a summary of everything that we had in the notes. So the homework that goes with this lecture, the lecture takes a lot longer than the homework in Chapter 9. The homework that goes with this section is review questions, page 317, 1 through 6. And you can do practice problems, page 318. We're only going to do 1 through 3 for this lecture. So I will talk to you next time.